welcome to today's webinar, Ready to Reverse Engineer Your Reverse Engineering Process, being hosted by FARO Technologies and co-hosted by Octon. I'm Janine Charity Wright, your moderator for the day. Before we get started, let's cover a few housekeeping items. Today's webinar is being recorded and will be shared with our registered guests via email a few business days post-completion. Additionally, if you have any questions during the webinar, please feel free to post your questions in the Q&A section at the bottom of your screen. Now, let's get started. Please allow me to introduce today's presenters, Will Pitarello, who has been with FARO Technologies for over 9 years and is a Senior Application Specialist for the 3DM segment. Will champions our demo studio and has been involved with the tech and biotech sectors for well over 20 years. Greg George is an applications engineer manager at Octon. He has been in the 3D scanning and engineering market for over 17 years. In his current role, he is responsible for supporting the Octon Geomagic software suite. Greg and his team are responsible for supporting sales with training, presentations, support, and consultation. So without further ado, Will and Greg, take it away.
All right, Janine. So first and foremost, thank you very much for that warm introduction. Thank you for taking a bit of time here out of your schedule to watch this webinar. There's a lot of effort involved in this for us. We're proud to be here with you and to present this webinar on reverse engineering today. So, Gigi, the band is back together, right?
Yes, we're at it again.
We're gonna do this again. But this time around, guys, make no mistake, there's no lounge chairs, there's no fancy backdrop. It's just us, our parts, our FARO arm, the granite cart, and we're gonna show, now we're gonna get down to the brass tacks of it. We're gonna get down to the nitty-gritty of reverse engineering, show it to you, the process from beginning to the end. And there's a lot of anticipation here, Gigi, because we've been talking about this with our customers for about 2 weeks. A lot of them, hopefully you were able to make. But like Janine said, this is going to be recorded for us. Before we start on the agenda for today, shout out to our man there, Mr. Derek Beebe up in Michigan, up in the trenches, right? The jungle territory of reverse engineering and inspection. Derek champions as an account manager up there, and he was kind enough to upset his little daughter here because he took apart a piece of her snowmobile so that we could reverse engineer. So Derek, we're gonna make sure we're gonna do this and we'll send the part back so she's happy again. But thank you for taking your time and doing that for us. So covering the agenda today, we're gonna talk really quick about FARO and Octon for you. If you don't know our companies, just to get to know us a little bit. We're gonna show you the process, right? Capture the data, analyze the data. We're gonna replicate a part and then revise a part, because that's what we can do. That's part of the reverse engineering process. We 3D print it, as you can see. We actually have two parts that we were able to 3D print, and then we're gonna finalize with an inspection, because it's gonna be hard to talk about reverse engineering and not talking about inspection, because they kind of go hand in hand. As customary, folks, we're gonna have our Q&A session at the end. Hopefully we're gonna have good time to respond to your questions, but if we don't, we're gonna get back to you via email and try to solve all pains that you have and issues and questions about this webinar. Keep an eye out, as customary again. There are gonna be polling questions throughout the entire webinar, because we wanna hear about you. We wanna understand what kind of process you are involved in and how we are able to help you. So without any further ado, let's go and talk to you really quick about FARO. We've been around for about 40 years, 43 years to be more exact. We are an all-American company with global presence in EMEA and APAC, manufacturing facilities in the US and in the Far East. We are the original inventors of this product right here, the FARO arm, which has been greatly improved throughout the years, of course. But since then, FARO went on to develop laser tracking technologies, laser scanning technologies to help out not only in 3D metrology, but also the folks in the AEC business, architecture, engineering, construction, and most recently on the PSA arena, public safety, the forensics markets, okay? FARO is not only a pioneer of this technology, but also a leading player in 3D metrology, imaging, and realization technology. We're super excited that our future, we're embarking on a new era as our new CEO under his leadership, Mr. Pete Lau. And we're excited. We can guarantee one thing: we're going to continue doing what we do best, which is bridging the digital world and the physical worlds. And that is a good thing.
Awesome.
Gigi, what can you tell us about Octon?
Yeah, so I'm from the Octon group. And Octon consists of 3 separate parts. We are a software-focused group under the 3D Systems umbrella. And in the software group, we have 3 different types of software. So our Geomagic product line, which we're highlighting today, which is the scan-based products. We also make some printing products like 3D Expert, which is a printing prep and slicer. For the metals, primarily the metals group. And then we also have a MOS product as well that controls the manufacturing operating system. So I'm from the Octon group, and today, of course, we're going to be talking about the scan stuff. But yeah, we're under the 3D Systems umbrella.
Got you. We're going to have an opportunity to look at the Geomagic software and something else regarding the 3D printing process, correct?
Exactly. Yep.
All right, cool. All right, so just in time for the first polling question of the day, right? So Janine is going to put that up on the screen for us, and we're going to be able to respond to that first polling at this time.
All right. So for poll number 1, do you have challenges that come from measuring complex geometries, surface finishes, or material properties?
Pretty common challenge in the industry. Parts are not only prismatic, oftentimes, especially what we're dealing with here, parts are going to have complex geometry, so that presents a challenge in itself.
Yeah. The complexity of the things that you're trying to measure are often, that is the number 1 hurdle, right? Besides just the surface finishes and all that. So
Yep.
Well, it looks like, guys, it is coming in pretty heavy on yes, but I don't know where to begin. So I think they are ready to hear what they are going to learn here today. I'm going to end that poll, and I'm going to just share the results with everyone very quickly. The answer to the question from the audience is yes, but I'm not satisfied with the tools that I'm using. 34% of our audience gave us that answer. 58% of the audience said yes, but I don't know where to begin. And then we have 8% that said no. So we have a good variety going on here. So I think they're ready to hear what you have to say. I'm going to stop sharing the results. And you can close the poll directly on your computers by clicking the X in your top corner. Back to you, Will.
All right. Thank you, Janine. So absolutely, right? Before we go and show you how, I love the next sequence of slides, guys. Bear with us, because I guess the first question we need to respond is the why, right? Why you're going to deploy these process reverse engineering. We can talk about application parts, but Gigi, you have the floor.
Yeah, so we have, on this slide, we're really talking about 4 different reasons why people are reverse engineering. Now, this is not a complete list. There's lots of different reasons why. These are 4 that are kind of related to our application today. So I think covering some of these will set the stage as we answer the I don't know where to begin with the poll question that we just talked about. A lot of this stuff will start to answer those questions, and we'll go through a few of these here. There are lots of different reasons why we reverse engineer. For the first one with the guitar, there are instances where sometimes you've created a design by hand or by a different method, right? And you need to capture that shape, that object, and then bring it into the digital world in order to scale up manufacturing, in order to go ahead and move it to a different type of manufacturing, right? So with that one, taking a scanner like this, I can go ahead and scan it and bring that into the digital world. So take an older type of manufacturing like castings, or in this instance, a guitar, maybe that was handmade, and bring it into the digital environment.
Kind of like touching on the world of art, right? Basically almost craft, handmade type stuff.
Exactly. Yeah. So that's one example of reverse engineering there. The second one, this is a little bit different as well, just to get everyone's mind thinking about different kinds of reverse engineering applications. The second one, it might be hard to see from the picture, but that is a scan of an off-road vehicle, right? And sometimes you scan something in order to design around it, right? And in this instance, that's a roll cage inside of the scan of the vehicle. So I'm not reverse engineering the vehicle itself. I'm just reverse engineering for clearances and contact points.
So not strange to the world of racing, for example, race cars. We did a bit here not too long ago on drift cars, right? So
very familiar application there. So the third one is designing mating parts. So a lot of people are familiar with the aftermarket parts like the floor mats in this example here, but scanning somebody else's product because you make a complementary product that fits to it, right? So scanning is excellent for that. As you can see, these are very complicated shapes.
Yep.
And if you need to make an aftermarket part, you can design something directly off that scan data to mate to the objects, right?
And we can think of what we did here, right? That could be falling into that category if we're gonna fit a modification to put maybe a cell phone on the dashboard of the snowmobile or any other vehicle, right?
Exactly, and you'll see a theme why I picked these throughout this webinar, because these specific applications, some of them I utilize that style of reverse engineering for this specific application.
Yeah.
And for the final one, there's another one where maybe you have tooling that you've designed and you've manufactured, but in the tooling world, a lot of times there's an operator or there's the machine shop that has to make corrections to the tool over time in order to pull a part properly, right? In order to stamp a part or mold a part. So they make manual modifications that are based on the expertise of the tooling group. And then sometimes those don't make it back into the engineering department. So that last one is an example where manual modifications were made. You can scan that and then update the original model that engineering is using.
Yeah. I'm thinking guys that are super experienced and they have the tribal knowledge and they do by hand. And
exactly.
For those folks on the survey, like the calipers and micrometers that you have to struggle a little bit in that world.
Exactly, and this kind of brings those two teams together, the engineering world that designs something in the ideal world, and then the practical people out on the machine floor that are making changes to the die itself.
Got you. Moving on to this slide, right? As built versus design intent. It's a little bit of a given, but I was curious when we saw that for the first time, because in the world of mechanical parts or in the world of architecture, for example, the as-built is the as-built conditions of the building or the way that something was constructed, the same thing in terms of part, right? And then what the engineer had in mind when they were designing it.
Exactly. So I think a lot of people inherently understand this concept, but we highlight it that reverse engineering can be divided into two categories here. You may scan something in order to duplicate it exactly as is, as you talked about, or you may scan something in order to capture that part to infer what the design intent originally was. And when I say that, sometimes people are a little bit confused. That clamp that's on the screen is a great example. You scan that clamp could have been a part that failed the inspection process and was laying around the shop. And if you scan that and duplicate it and start manufacturing that one, you've basically duplicated a poor part, right? So you actually want to scan it, correct its measurements, and make a perfect part from it, and then manufacture good parts from there. And this is just pointing out that there are reasons why you would want as-built and design intent. Either or on the last example there, you can use both of them. There may be parts of the part you want to be exactly like the existing condition, but then make changes to it to add some design intent to it. And that's what that why not both is, is pointing out.
Gotcha. So basically, when parts are created it's impossible to create them to the perfect level. They're going to be at fault or defects.
Yep.
The as-built versus design intent is going to bring that together and focus on improvement, absolutely.
Exactly, yeah, because the whole goal here is to make good parts, right?
Yep.
That pass inspection and don't fail.
So this slide, guys, it's a little bit of it's a lot on the slide. I like slide with few information, but there's just no way around this because this is so important in the world of reverse engineering, right? Capture the data. What do we do with it? Where do you go from there, Gigi?
Exactly. I use this slide on purpose so people can reference it later if they want to look back and watch it. But this is a slide that really demonstrates that you can categorize the different types of deliverables from reverse engineering into 3 major categories. Now, there are more slight variations of these, but really I'm just pointing out when you look at a reverse engineering project, what am I trying to achieve with it? And these are 3 categories. So many people want to reverse engineer something to get the data into CAD or into a CNC software or into additive, as we're talking about today. So yes, there are variations on these workflows, but I will say what the solution that we're showing today is you can actually go all 3 of these paths. You can take all 3 of these destinations here, and just identifying that at the beginning of the process. Am I trying to go to CAD, or am I trying to go to CNC or additive, which is 3D printing, right?
Yeah. And I get, folks, a lot in a web demo. The question is, so yeah, you have the data. What is the format? Well, the format depends on the intent. What you're going to do with it. And I take it, obviously, that the software is going to export all types of formats for CAD, for CNC, for additive material.
Yes, exactly. So the products that we're going to talk about today will go into each of these in a various different ways. The CAD one is the one that we're going to highlight mostly today. But when we take this data and process it, we're going to go directly into CAD as native entities using our live transfer tool, which we'll describe in some of the clips to come.
Okay. So, guys, really, right? Collecting the data is going to depend on the size of the part. It's going to depend on how accurate you want to be. There's a tool for every job, as you can see in this slide. We use the FARO arm for this part because it makes sense. The world of metrology requires a lot of accuracy, its parts. But if you have something bigger, for example, like the granite card that we're in here in this studio, maybe the Freestyle, which is the other kind of like handheld device, would be feasible because it's a little bit more hands-free. It's going to work on larger parts. And finally, if you need to create an as-built of this studio here, this space or a building, then the laser focus, which is the device there, would be, regardless of the device that you're gonna use, and the end result, the data is gonna be cloud. And after that, what kind of process? What is the process there, Gigi?
Absolutely. So when these types of scanners came around, when FARO started putting the laser on top of the arm or the focus, you're creating these mass clouds of 3D measurements, right? And honestly, the CAD world was never ready for that because you have these files that are collecting tons and tons of data, very accurate measurements. And CAD is designed for very simple, smaller amounts of information, right? So that's where we brought in this DesignX product, where Geomagic developed this product. And really what it is, it's a mix of our scan platform, our scanning kernel, and then a CAD kernel all into one software. So we're bridging that gap between the scanners and all those deliverables that we introduced a few minutes ago. And what we're going to do is take all the data from these amazing scanners that capture just millions and millions of measurements, process them into models that then we can output into CAD, CNC, or additive, right? And that's really what DesignX is designed to do, is take that process and simplify it.
Yeah, and there's plenty of software in the CAD world or CNC or additive material to choose from. You know, depending on what you have, each software will be friendly or not to certain types of extensions. So being neutral there. I'm
Yep.
sure, yeah.
Yeah, we're neutral. We work with every single format you can imagine, depending on what you're going for. So we even, like I said before, we live transfer directly into CAD as native models, native entities. Or in the additive world, we can save out all the different mesh formats that are out there. So,
okay. One of the questions that I find the most in a web demo is I work heavily in the world of manufacturing mechanical parts, high accuracy, transforming the data into CAD. There is a process involved, right? And usually I hear a lot about meshes and things like that, but this slide is suggesting something different, right? Is this slide suggesting that cloud can be worked into surfaces as CAD as well?
exactly. So I bring that up because you scan as a point cloud initially. You can scan as a mesh too, but you can work with meshes and point clouds inside of DesignX. And for focus applications, like you talked about, maybe if we scan this entire room, it's maybe not necessary to take that point cloud and connect it together into a polygon mesh. Maybe you just leave it as a point cloud and extract the model information that you want, draw the floor plan or whatever it is, straight from the point cloud and save time. So there are reasons why you may just leave it as a point cloud or convert it over to a polygon mesh. And again, the goal there is to get it over into a usable CAD format most of the time.
Okay. All right. So now we're gonna take a look at Derek as he scans a little bit of the part or the snowmobile. He's actually in his metrology lab / garage doing that. But the first thing, we've got the part here, right? But the thing that we're seeing right now is that Derek is scanning the whole snowmobile. Why would we want to do that in that situation, G?
Yeah, so I mean, because it's quick and easy to scan something of that size with that arm, what we can do is we can scan the entire sled, scan the part itself, and even scan individual pieces of it and assemble them together digitally inside of our software. That way you can hide and show and turn on and off different things.
Interference and checking for problems before they happen in the real world.
Exactly. And then if I do design a new part directly on top of the part, you have the entire sled that you could run, analysis on it, CFD analysis and things like that, with having the entire scan data set. You can actually check clearances of the steering wheel, all that is possible if you scan the entire thing.
Got you. On the hardware side of things, folks, I just would like to point out, Derek right now has got his arm on a tripod. Obviously, his arm is a bigger arm. I know it's a 3.5 meter that he used. In contrast to what I have here, I've got a 2 meter arm. The way that arms work, I'm sure a lot of you know that. So if this is 2 meter, I got 1 meter each side. So he's got a 3 meter arm. So he got half on this side. So you put the arm close to the part, and you're free to move around. The other thing that I notice is I think Derek prefers, if you look at, I know it's kind of hard to see on the video, but if you look on the video, he's actually using the laser scanner on the front of the arm. So he's not using the scanner at the top, holding it kind of like a pistol. So he has a little plate at the bottom that he can put on. And look how we change the way that the arm is configured or held. If you have a part like this, no big deal if you have like that gun type of style, right? But if you have like the snowmobile close to you, maybe to go underneath, this offers flexibility. And you may think this is not a big deal, again, for a small part, not. But depending on what type of parts or structures you're scanning, this can go a long way, right? So this is what he did. And I thought this was really interesting to see because it was a matter of preference. The other thing that you're seeing here now that Derek did, he used the 8-axis system of the arm, which is nothing more than this rotation table that I have here with me as well. I actually got the same part on top of mine, but notice a difference, right? He's got a 10-inch plate and I have a 20-inch plate. So I have a bigger plate than he had. So he used one of our accessories to hold. A little bit of hot glue there goes a long way as well. So he's holding the part on top of that. And why he did that? Because the 8th axis allows for the movement of the part, but not really relative to the arm, because the 8th axis is another encoder of the arm itself, much like the first one in here. And that allows freedom of movement, and I can scan with much ease, better accuracy number, and things like that. So on the part side of things, he got helped, well, not only from the 8th axis, but also he got help from Adrienne, his little daughter, that's his metrology assistant.
Yeah,
so
junior metrologist.
Junior metrologist, good job there, buddy, because I can't get the 18-year-old not to cut the grass in the house. So good going there. All right, so now we collect the data. Okay, so what we're gonna do now is we're gonna see how to process that data. So that environment, folks, this is Geomagic Design X, and I think what's going on here, well, Gigi, why don't you take up?
Yeah, why don't we talk about it?
Yeah.
What we did is we had him go ahead and scan the entire thing. And this is really just demonstrating how if you scan the entire part, you can go through and we have all these different tools to edit. I can separate the pieces into different objects in the tree. I can crop things. I can clean it up in a variety of different ways. And you see here, I got a bunch of different tools that are operating where if there was a piece of lint or dust or dirt on the surface that I do scan, or I even capture part of my hand in there,
Gotcha.
I can erase things.
In one of my notes, I had it here that we were talking about this yesterday. How important is the quality of the data that you're collecting? Is the device that is collecting, and the quality of the data itself, right?
Yeah, absolutely. What you're trying to do is make sure you scan everything you need. And you'll notice that we overscanned, we captured some of the floor. And you want to capture good, accurate data. And having a device like this that captures extremely fast, highly accurate data, when I zoom in, you'll see the detail that's in the scan, right? And you can, again, just remove defects that may be in the surface. And it's so accurate, it's capturing all those different defects on the surface, whether it's dirt, scratches, or anything. And then we give you the tools inside of our software to erase those, smooth them out, correct them, and piece the objects together. So really, when you look at this, it's just a tool that's like a full-on editor. So oftentimes I'll relate it to like a Photoshop for images, right? You can piece things together, you can merge them, you can crop out different areas that you want, you can align them together. You see here that I'm actually cropping down just an area that I only want to work with this specific region. So if you have areas that are lots of occluded areas of the scan, you can hide other areas and simplify it down and do hole filling and correction of parts that were overscanned or whatever.
Gotcha.
To create a nice clean mesh.
There is something to be said, Gigi, about the surface finish of parts, right? I mean, in talking to Derek and understanding the process he did, I know that he engaged the HDR, the high dynamic mode of the scanner in the software. We are pioneers of the blue laser, so parts like these of black and shiny or shiny parts, it's not a challenge for this technology, but there's something to be said about this. You want to get quality data, and that's what I'm thinking why Derek engaged that HDR mode, so we had that quality data for this part.
Exactly. I think sometimes we've both been scanning and processing the data for so long, sometimes we overlook the capturing process, and many people that are taking the poll, they don't know how the process works. So hopefully these videos and this explanation shows you how we captured the data and how easy it was for somebody to capture that data all the way in Michigan and send it to me in North Carolina. I edited it and I sent it over to South Carolina to print the part. So like this ability to capture this data and send it around and work with it extremely easy is another benefit of what we're doing here.
All right, so we have the data, we processed it, and now we're gonna well, we're going to show you how we're just simply replicating the part or copying the part. There is something more after this, which is basically we're going to revise the part or change the part, but I want to focus on this specific video right now. So replicating the part, making the part live in the digital world so we can make CAD out of it or whatever reason, right?
Yeah, absolutely. So what we're highlighting now is we worked on that capture side and editing the scan data. Now we're transitioning into how do I extract the geometry from the scan data, right? There's a lot of mystery behind this. A lot of people have a lot of questions about the modeling side. So usually this is where I get the most questions here. We captured the scan data, we got great scan data. All of the tools that are inside of DesignX that allow me to create regions, that's what those colors are. I select that region, and then we can extract CAD information from the scan data. In that instance, I was using a loft wizard, where we select that region, we say, put a surface loft through that information, and our software will create loft cross sections automatically, do a 3D comparison, allow you to make changes, and you even see that we get feedback there with our deviation analysis to make sure that you're following the scan exactly, right?
Right. So that language you're using, right? Lofting and sketching and extruding. Exactly. This is language of CAD software, correct?
Exactly.
So if you have knowledge of CAD software or no CAD software, Geomagic DesignX should not be...
It should be very familiar.
Very familiar with.
Both interface-wise and all the terms that I'm using here. As we talk about this, if you've used any sort of CAD package like Inventor, SolidWorks, NX, CATIA, any of those softwares, right? When I say, let's do an extrude or a revolve or a loft, these are familiar things to you, right? These are different construction methods. And we're fitting these surfaces directly to that mesh because the scan data is a different kind of model, right? It's a 3D polygon mesh. And these CAD softwares are using NURB surfaces, so non-uniform rational B-splines. We don't need to get super technical about it, but it's a different kind of 3D modeling family, right? And what we're doing is we're extracting that information and getting it over to the CAD world. And most CAD people are very familiar with that world, right? So usually, I'm just speaking the language, showing them how to get that CAD information, the lofts, the sweeps, the sketches, all of that inside of the CAD environment, so they can do the things that they already know how to do inside of their choice CAD software.
Gotcha. And once you have the final product, I remember from the last webinar we did, you touched on something called live transfer, right, on Geomagic.
Exactly. So I know that most people, when you design something, the end result isn't a DesignX file, right? We want to go make whatever it is we're creating in here. We want to make it, and there's different ways of creating it. Most of the time, people actually want to get it over inside of a CAD package. And in order to get it in a CAD package, to make it as easy as possible, we made a tool called the Live Transfer tool. It's up there in the top of the ribbon. You'll see a SolidWorks logo, and there's a stack of all the different CAD packages that we support. And really what that does is it allows you, if you have the CAD package installed on the same machine as DesignX, if I created a sketch and then extruded it, our software will say, okay, draw that sketch inside of SolidWorks and extrude it this same distance, right? So we actually translate that with a live transfer. That's why we call it live transfer over inside of the SolidWorks package. That way, once you finish modeling, you have a native CAD file that anybody in the organization that uses that CAD package, let's say it's SolidWorks, all the SolidWorks designers that are in that group can now work off of that same SolidWorks file in their native software that they're used to, right? So that's what the live transfer tool does, and we're the only ones that have that elaborate tool that allows you to model the whole thing and move the history tree all the way over to CAD package.
Got you.
CAD package.
You don't see, for example, if somebody has SolidWorks or some of our listeners, they have any CAD package, the Geomagic DesignX will complement, not substitute their CAD packages, correct?
Exactly. So just to highlight some of the differences, just so everyone knows, we have all the scan platform and modeling tools, but we don't do assemblies and drawings. That way we're complementing the CAD package themselves but not necessarily competing with them, right?
Gotcha.
We don't have any of the analysis tools and things like that.
Got you. I just thought this would be nice to highlight. Now comes time to revise the part. There's a lot going on here that happened in the video one, right? We're just gonna go through this video here, and Gigi's gonna talk about what's going on here.
So yeah, just to summarize, video one, you saw that we were extracting the shape of this part itself, right? And that's just showing the reverse engineering process. If I was gonna reverse engineer the interfacing surfaces of that part in order to hand them over to SolidWorks to create a design. Now in this video, what I'm showing is I can actually use the scan data of this part and do a design directly over top of it without converting it. This is basically kind of an alternative method here. You can reverse engineer the part itself, or I'm designing around the mesh itself here, as you'll see as the video progresses. So I'm using a lot of the same tools, but we are doing the design of the replacement part inside of Design X. And you see I'm doing lots of surface drawing and fitting directly to the part, but I'm not reverse engineering the scan itself. I'm creating a new design, as you'll see as it progresses along. So you'll see that I drew that sketch and I extend it out. And once we convert it to a surface, you'll see that I'm not reverse engineering the part, I'm creating a new part that mates to it, right?
And that is the case. If you want to maybe put room for a cell phone or extend it, you know, the windscreen a little bit, you could.
Exactly. And that's really what I did in this instance is we designed an alternative aftermarket part here, right? So there is the stock windscreen for this, and then you could create an alternative smaller one, maybe one that has a cell phone mount or different types of mounts that you want to mount a GPS to it or something like that, if you still use those. You can mount those on here and create your own design that interfaces exactly with the scan of this sled itself, right? And you know it's going to fit, right? Because you designed it directly off of the geometry that was scanned.
Yeah, so folks, think of the possibilities, right? If you guys are watching us from different types of industries, as I said, recreational vehicles, motorcycles, jet skis, or mechanical parts that you're building, that you need to reverse, old cars, the antique market, right?
Exactly. There's so many legacy parts, legacy designs, and or new ones that you need to make a complementary product to that would require something like this, where you can 3D scan a legacy piece, make an alternative design, an upgraded design. Maybe it needs to account for new technologies that are being added to it. We see that a lot with adding new sensors to all kinds of vehicles and things like that. So being able to scan and design directly on top of the scan data and just skipping reverse engineering the part itself and just skipping to the design around the scan data, as we allude all the way back to that original reverse engineering application I talked on one of the early slides, that sometimes you just want to design around something and design something that fits to it, right? And that's really what we're highlighting here, is the ability to create this design directly on top of the scan data. And then when we're done, you can send it over to CAD, which is a huge benefit here. But the other thing is I can go ahead and convert this and save it for printing, which is what we ended up doing in this instance.
Yep. All right, so there's a lot of material there that we cover. We're gonna give it a pause now to go into a polling question number 2.
All right, here we are. Question number 2. Do you currently use 3D scanning software in your design manufacturing process? Yes? No? What's 3D scanning software?
I'd be curious to see the results of this one.
Yeah, this one will be interesting.
Wow, we're at a 50-50 split right now.
Yeah, and folks, believe it or not, the amount of customers that I see, both in the US and abroad, and in Europe and Latin America, there's lots and lots of folks out there not using anything 3D in order to capture, to collect data, to scan. It's completely by hand with calipers, and it's a big pain because it's very
Takes a lot longer
lengthy. Yep.
to extract. And when you have the scan data, a lot of times you catch mistakes, right? So when I design this around the scan data, I can make sure that I have enough clearance for whatever that maybe I wouldn't understand if I just created discrete measurements with calipers or a height gauge and I modeled it. I can't see it in context.
Okay. Well, we got the poll completed. Looks like we have 60% of our audience saying yes, and the other 35% saying no. All right, if you want to close that box on your screen, just click the X in the top right corner. Back to you, Will.
Thank you, Janine. So guys, after the whole process, right now, let's take a look at 3D printing. Maybe not your cup of tea, maybe not what you're going to do, but this is what we did with this part. We want to highlight it, and there's pretty exciting stuff happening right now in the world of 3D print. So Gigi, what's going on here?
Yeah, absolutely. So what I did is after I created my design, I went ahead and sent it over to our printing department, and they were able to load it into our software. This is 3D Sprint software. So it's the software that we have that covers all of our printers. And you'll see there, it even has the model number written on the bed there. So it's our SLA 750 dual. So it's a dual laser stereolithography machine. And he laid it out, even duplicated it, added supports. And then what we're seeing right now is the preview of the cross sections that it's going to use the laser to trace out those cross sections once we get over to the printer. So you'll see here, that's zooming in to see the sections. Now we're actually on the machine, and with this machine, we have this AMX material that's a stronger material that allows you to, we can actually put this on the sled itself and use it. So what we're seeing now is the way this specific device works, you have a vat of liquid material, and then the laser hits each cross section and cures just that area. And what happens is it cures it down into the fluid. So what we're witnessing right now is once it's complete, we then raise the part up out of the fluid. So you see there, as it prints, it goes down like it shows there with the video. And then when you're finished, we raise it up out of the material, and it just prints section by section, layer by layer. And with the supports, you see it's got some supports holding it to the tray there. And then they take this out and they process and remove the supports and hand the part over to us.
And how do you call that machine again, the 3D print?
This is an SLA. This is the specific, there's different kinds of print engines, different technologies, right? We print in metals and all different sorts of plastics, nylons, different things like this. This is our SLA. That's the technology that our company invented in the 80s, right? So we've had this technology forever.
As far as 3D printing, is it your opinion that we're quite there, kind of replacing machine in the world of manufacturing and aerospace? And are we replacing machine parts?
Yes, they're replacing a lot of them where it makes sense, right? There are certain times where traditional manufacturing, subtractive stuff makes sense still for scale purposes. But really, the additive world is just coming alongside the subtractive world and giving all the engineers and manufacturers different tools to tackle different problems, right? So the additive world is creating now, it used to be that they would call it rapid prototyping, right? But now we're manufacturing parts that can be used with the additive process. So that's why it really transitioned into additive manufacturing from rapid prototyping or 3D printing. We're really kind of transitioning that naming because these parts we can print in metals. These are parts that we use every day now.
Gotcha. Okay, so the end, or we have another poll question. Janine, please.
All right, that was a quick one. All right, poll number 3. Do you currently use quality control tools? I use 3D measurement tools. I use manual tools. I combine both 3D measurement and manual tools.
Yeah, well, they get to it. I mean, I see still to this day, believe it or not, 50-50 out there, or, a lot of people still use traditional tools.
It is amazing how many traditional tools you still see out in the market. And I'm not devaluing them whatsoever.
Yeah.
They still have a place. But it is pretty crazy when you have these highly complicated parts, being able to use more elaborate measurement technology to speed up the process and get better results.
It's time consuming, and especially organic surfaces, like complex surfaces.
Exactly. The more complicated it is, the more time it's going to take to measure with traditional methods.
All right, I'm going to end that poll. Guys, we have 59% saying I combine both 3D measurement and manual, but we do have 41% that are still using manual tools. Remember, if you want to close that poll box, you can click that X in the top right corner. Back to you, Will.
All right, thank you, folks. So what we're going to do now, we're going to get to my cup of tea here, because this is what I thrive. I love the inspection portion, and now we're not living in the world of Geomagic design anymore. We're living in the world of Geomagic Control X, correct?
Absolutely, yeah. So what we're doing now, and again, this is your wheelhouse. This is where you're used to living.
Familiar with the color map, right?
Yes, you're very familiar with the color map. What we did is we took the manufactured part, the printed part here, and we are 3D scanning it again and bringing it in and comparing it to the CAD model from the design, right? And what we're witnessing now is the 3D color map to create dimensions and see how closely we printed it out and how closely it matches the CAD model.
And I'm thinking you can pick and choose your best fit alignment, your feature alignment, your different types of alignments.
Yep, and even have multiple alignments within an inspection, right? If you want to have multiple alignments, you want to do a color map with the best fit and then do feature-based in order for the GD&T. Like, there's lots of different methods here that you can do. So the Control X is a different software in our portfolio. As you can see, it looks very similar. It's built on the same platform. It just has green as the highlights instead of the red. And its deliverable is those dimensions that we're talking about. So what we're doing now is pulling out, I'm just manually making dimensions. And everything that I dimension manually right now is automatable. So if I say, what is that diameter? And I just click on the CAD model and pull out a diameter. First of all, it's dimensioning based off the scan data at the same time as it's dimensioning the CAD model. But two, it's just creating a program for us as we create the dimensions here.
Gotcha. So let me just, it was interesting yesterday when we were discussing this, folks, and I just want to share this with you. The ARM also gives you the probing capability. Obviously, you got a probe in there, you can probe and scan. This part, couple of holes around, and it's pretty rigid, so it's fair to say that I could probe this part, distance between holes, and probe holes and understand that. Because the ARM gives me that flexibility. That's one of the superpowers of the ARM, scanning and probing together. But Gigi, you said something that raised my curiosity, right? I mean, yes, I could, but for this part like this, due to the nature of the part, it makes sense for me to scan. But you took it a little step further there, right, regarding the scanning data.
Yeah, so the scanning aspect of Control X, that's in a way our native format. So this software evolved later in our portfolio. So we designed it around scanning metrology and probing metrology at the same time. It wasn't a probing software that we added scanning functionality later. This is one where we designed it from the ground up to handle scan data as native entities. So it's not going to get bogged down with huge scan data sets. It was initial design.
Because that's usually the concern, right, folks? I mean, if you're scanning, yeah, it's a heap load of information. It's a lot of data, and people are concerned about, the power of the computer and things like that. So some people shy away a little bit from scanning.
Yeah, sometimes people are afraid on the metrology side of scanning a part. But again, we designed it from that. We're very much at home taking the scan of a part and doing metrology off of it. We were built with that in mind from the beginning. And you can see here that we were able to bring it in, make measurements, do the color map, and export a report.
Report it out, yeah. Yeah, we saw that. We saw that action. Okay. So did I miss anything? No, I think it's straight to poll question number 4. I think we reached the end, guys. So just before we go there, collecting the data, the manner in which we collect the data, the quality of the data, processing it, revising the part, replicating the part, printing the part, machining it, inspecting. That is the full workflow that we wanted to show and talk to you about it. I think we're doing good time for poll questions, Janine, and Q&A.
Yes, we are doing very good on time. We do have quite a few questions from the audience, but before I get into those questions, I do have one more poll for everyone. And that poll is simply, what can FARO do for you next? Provide me with a quote or an estimate, schedule a demo, provide me with more information, or nothing at this time. I'm going to leave that poll up for a few minutes while we just jump right on into those questions. As I said, we had quite a few questions in the audience. So what is the weight limit of a part on the 8-axis?
Great question. Regardless of the plate, remember that I said I have a 20-inch plate here in the studio. Derek was using a 10-inch plate. Regardless of that, the capacity is 223 pounds. So for all intents and purposes, if the snowmobile weighs that much, I mean, and if I can make it fit, obviously the part cannot move on top of the 8th axis so much that Derek, for example, had that fixturing kit that is an accessory for us. But if the part does not move on top of that and it fits the 8th axis, by all means, scan it with the 8th axis. 223 pounds is your answer.
Okay. How long did it take for you to model the part?
Oh yeah, so once I received that scan data, I brought it in, and it took me probably about an hour to model the part.
So it's really not that gruesome work. I mean,
no. Now I will say that yes, I work for the company and I model stuff every day, but I also point out that again, if you're a CAD user and you're familiar with all of your common CAD packages, you're familiar with how to model something, the transition over to DesignX is pretty easy because you understand what an extrusion is and how to draw sketches and things like that. So breaking down a part into its components and modeling it is a lot easier. So that's really the prerequisite. If you have an understanding of 3D CAD modeling, then DesignX will make a lot of sense to you.
And training is available all over the world, right?
Exactly. We do all the different kinds of training, whether it's in person, virtual, right, and over the web. So, or we have people come to us in our facilities.
Gotcha.
Okay. How small physical dimensions were the defects which you just removed?
Some of them were in the range of, I would say, like 1/4 of an inch in size. And depth-wise, I mean, it seemed like there were some that are like 10 thou, 20 thou, 30 thou deep, thousandths of an inch. That's it. And again, some of that stuff was literally just dirt. There's lots of reasons why there would be surface defects on that part. But this part, as you can see here, how big would you say this is? I mean, I designed it. I don't even know how big it is because I designed it right over top of the stuff. So I wasn't even
scanner, right? Yeah.
thinking about how big it is.
Say give or take about 400 millimeters, more or less.
Yeah, 400-ish.
Okay. What size is the quantum arm that you have there with you?
Great question. This is a 2-meter arm. Okay, so 2-meter arm, again, 2 meter is the volume of the arm. So the arm will reach 1 meter this way, 1 meter that way, 1 meter up or 1 meter down. So if you have, say, for example, a 2-meter part to measure, you're going to put the arm in the middle. You're going to go halfway. that way and you're good to go. As a matter of fact, a 2-meter arm, spec 2 meters, great question. Physically, the arm is a little bit bigger. It's actually 2.6 meters. And that is because we did a change in the joints of the arm, guys. The arm now has a true clavis mechanism joint. So the 2-meter is with the 7 axis looking down, but if I open up, I'm able to gain a little bit more. This is a 2-meter arm, and Derek used a 3.5-meter arm. Good question.
Okay.
Oh, Janine, sorry.
Yeah.
One more thing, just to complement the question, right? Just because you have a 2-meter arm, it does not mean that you cannot measure a 3-meter part. You can. Absolutely. Any model arms, any size arm will allow for the move device, or commonly known as the leapfrogging procedure. Just to measure a couple of features in position 1, switch the arm to position 2 so you can measure the rest of the part, and before you do, you remeasure those features really quick, and the software will snap the coordinate system back to its original position. So this is the leapfrog. And again, I like to say that because sometimes you want to move not the arm because of size, but you want to move your part because of reach. Maybe you have something to measure on the underside.
The other thing I point out is the 8th axis can extend the volume, because if the part is sticking out this way and I rotate it around, I can bring it in the volume of the arm.
Yep.
And it almost extends.
Absolutely.
I mean, it does extend the volume.
So yeah, because with my 2-meter arm, the part sits in here, and I don't have, like Derek did right in the video, reaching around. If I don't have to do it, I'll stay in this one position. I'll make the part kind of come to me.
Make it come to you.
Yep.
Yeah.
Good question.
Awesome. Okay, this is a little more deep here. HDR was mentioned to improve data quality. In Focus S-Line scanners, does the HDR mode improve the measured data, or is it only affecting the quality of the color data?
That is a great question, and I'm going to go with quality of the data, right? Remember, the point cloud is single color, so the quality of the data will be best. You're not going to have so much outliers because the software is kind of filtering that. So that's the idea there. So
the term HDR is used in photography, and we also kind of borrow that term for the lasers, because lasers are a form of photography, honestly. But when we say HDR, what we're doing is we're actually we're bracketing the exposure of the camera that's looking at the laser for multiple settings and blending them together. That way, you're essentially saying a shiny surface, it's exposing the surface multiple times at different settings and then blending them together to increase the accuracy that you're referring to. Yeah. So that's what, when we say HDR in this context, we're talking about accuracy and surface finish.
Yeah, because if you have reflective points, remember, when you try to extract something with the outliers, that's going to throw off your measurement. So at the end of the day, you're improving on those areas.
Okay, guys, that looks like that's all the time that we have for today. But before I go into our closing, you do have a fan base in the audience with a few people just waving hello to you. So hello to you, Will and Greg, from your audience members. But again, thank you for today's webinar. It has been very informative. And we also want to thank our online guests for attending today. Ready to reverse engineer your reverse engineering process. As a reminder, today's webinar was recorded and will be shared with our registered guests via email a few business days post-completion. We look forward to hosting you again at a future webinar. Thank you and have a great rest of your day.